Okay, folks, let's calculate the power of hydrogen, aka pH, and that's what it needs. As mentioned earlier, you know the scale is 0 to 14. Typically, you can actually go below or above that. Yes, you can. Logs, pH is a log scale, and what that means is that every time you jump one on the scale, it's big. That's what really comes down to what logs mean. Logs are exponents. And so if you go from a pH of 7 to 8 and then 8 to 9, a pH of 7, which we know is neutral, right? Maybe, did we go over this? I think we did. All right, 0 to 14, let's write it down. pH 7, so if you're right here at 7, we'll expand this a little bit. Make this a little bigger. 0, we'll do this, 7, 14, how's that? Okay, this is neutral. This is like Switzerland. Nice and neutral. All right, when you go below 7, you have an acid solution. So this is acidic. So acid, acidic, and above here is basic. Sometimes you will hear the word alkaline. Alkaline means basic, same thing. All right, so 7 and above, basic, 7 and below, acidic. Most things that we consume are acids. A lot of things we consume, drinks I'm talking about. Your coffee, your orange juice, citric acid, coffee, tannic acid, I believe. You have a lot of different acidic solutions that you consume. And actually, if you just drink rainwater, you're drinking an acidic solution because lake water, stream, rainwater is acidic because it has carbonic acid in it. Maybe some sulfuric acid too, depending on what part of the country you're in. Acid rain, you've heard of that. So there is very, very, very few just pure waters. It just doesn't happen. I mean, we can make pure water, deionized water, distilled water, just pure water. But in nature, no. And most things we consume, no, not neutral. Acidic. People, when they acidic things taste sour. You take some Sour Patch Kids or some sour, we used to have these sour powdery stuff we used to, that's sour, okay? Sour, acid. Base? Base is, okay, acid base. Now bases taste bitter to people. Many people, humans don't like bitter taste. We don't like that, which we've developed that because many things in nature which are bitter are poisonous and not a good thing to consume. So most people don't like base. But acid? Okay, we're good with that. All right, anyways, moving on. So this pH scale is the power of hydrogen. And if you were to go up the scale to a pH of 8, then up the scale again to a pH of 9, then up the scale again to a pH of 10, you would say, well, you've moved from 7 to 10. NBD, right? No big deal. Yeah, it is, because this is logarithmic. What that would mean is that every time that you move up 1 in the scale, you're increasing your acidity, if you go this way, or your alkalinity, if you go this way, by 10, by a factor of 10. So if you go from 7 to 8, that's 8 times more basic than neutral 7. If you go to 9, that's another 10 times more basic. If you go to 10, another 10 times. Now you multiply those. 10 times 10 times 10, a pH of 10. Oh, 10, it's only 3 above 7. That's not a big deal, right? It's 1,000 times more alkaline. Because 10 times 10 times 10, it's a log scale. So what looks like small jumps are huge when it comes to the number game. Okay, all right, so here we go. Now these 3 equations we're going to be using all day, and actually next day, and the next day after that. These equations don't go away. So we have to learn how to do these. These are the basic equations. This is like learning, you got to learn how to do the mole before you can do stoichiometry. If you can't do the mole, you can't do stoichiometry. If you can't do these equations, we can't do acid-base chemistry. So we got to get these bad Larrys down. This one we've seen, the concentration of hydrogen and the concentration of OH is always going to equal 1 times 10 to the negative 14th. Okay, remember that. Here's our pH equation. Here's the POH equation, the power of hydroxide. You can measure things that way as well. Most people don't. Most people go with the power of hydrogen, but they're the opposites of one another. So if you have a pH of 8, then that pH of 8 is alkaline, okay? It's just into the basic range. So what would the pOH of that be? To get the pOH, what you do is to get pOH, you take pH and you subtract it from 14. And that gives you the pOH. So we got to remember this too. This is going to come in handy. If I want to switch back and forth between pH and pOH, just remember 14 minus pH. If you're trying to find pOH and you get pOH. 14 minus pOH if you're trying to get pH. So in this case, if the pH were 8, and all right, 14 minus 8. Anybody have a calculator? You did. Billy, what'd you get? 6? Okay, 6. Your pOH would be 6. Okay, it just reverses the scale is what you're doing. Okay, all right, so most of the time, though, we don't do pOH, although sometimes we will. We'll come back to it, but most of the time we're doing pH. But these equations we need to know how to do, so let's dive in and do one. All right, problem number dos. Numero dos, people. Numero dos on our sheet for the week. It says the concentration of OH ions in a certain household ammonia cleaning solution is 0.0025 molar. These are concentration brackets, remember. Give me a concentration. I'm not going to do pH here. This is concentration as well, but the easier way, there are two ways. There's more than one way to skin a cat. Remember that. So quite often you could use this one or this one, or this one or this one. You can do that, but this one is going to be easier if I just go ahead and do this, because here's what I know. I know the concentration of U and the concentration of U have got to equal that. It gave me a concentration. It gave me the concentration of the OH. Let's put it in. I bet the question is going to be, what's the hydrogen ion concentration? That's why they pay me the big bucks. Let's read. Calculate the concentration of the hydrogen ions. This guy. Okay, so let's go ahead and solve for this. It wants this. It wants to solve for that. So I'll put that as X. And I'm going to go ahead, when I do my math, I take out the square brackets and put the round brackets in for math. 0.0025. 0.0025. Now that's 2.5 times 10 to the negative third. And you can go ahead and put it in like that. Either way, it doesn't matter. It's the same thing. These two together have to equal 1 times 10 to the negative 14. Okay, so do the math, and we have the answer to this question. It's not hard. It's not hard. We just have to know, how to use the equation. It's not hard. So take this, divide it by that, and we'll get X. Now think about this before we get an answer. This is an ammonia solution. Water with ammonia, which is a base. It's a basic solution. The pH is going to be basic, which means we should have more OH than H, right? It's basic, so we should have more of this than this. So we have a number for this already. When we get this calculation done, this should be a small number because we know it's ammonia, it's basic. That means it's going to have not very much of that. Okay, hopefully that makes some sense. We will not have much hydrogen. The number for OH is going to be a lot higher. In fact, this is times 10 to the negative third. You know when you multiply exponents, you add them. So we could say 14 minus 3, this is going to be like negative 10 or negative 11, somewhere in that ballpark. It's going to be small. Let's do it. Oh, you need a log thing. You do. You need a calculator with a log button. Logs are easy. You don't have to know that they're exponents, 10 exponents of 10. You don't need to know that. You just need to know how to hit the button. Hit the button. All right, so let's see. This one, actually, we don't need a log button on this one. Divide. 1. Second function exponent. Negative 14. Divide. 2.5. Second function exponent. Negative 3. Enter. Boom. 4 times 10 to the negative 12th. 4 times 10 to the negative 12. I said 10 or 11. That was not considering the thing out in front, the 2.5. So that is small, right? I mean, think about that. That's a small number. I forgot. 4 times 10 to the negative 12. Look at that number. That's tiny. That's how much hydrogen you have. You have a little tiny amount. Why? Because it's a basic solution. You have a lot more of this, a lot more of the hydroxide than we do that. Okay, so we don't have a lot of hydrogen in there, and that makes sense. It's a basic solution. So that's the concentration. Now we could go on and figure out the pH of the solution. We won't do that because we'll do that in the next problem. But we'll leave it at that. That's my concentration. If I wanted to know the pH, I would take this hydrogen for the pH, and I put it up there, and I would do that calculation. All right, but we'll save that. Okay, so here we go. Part B. Part B, part B, part B. Get sniffly. Calculate the concentration of hydroxide. Ooh, good question. In 1.4 times 10 to the minus third molar HCl solution. So this is 1.4 times 10 to the minus third HCl. That's the concentration of the acid. It tells me that because it says molar, so I know that's the concentration. So I know the concentration of the acid is that. It gives me that. Okay. What's on the OH? What's on the OH concentration? So what is the concentration of the hydroxide? This time, the hydroxide is being found. That's X. I know that these two have got to combine and make 1 times 10 to the negative 14. Well, I need to put the H here and put it there so I can take it and then divide it into 1 times 10 to the negative 14 to be done with this problem. But they didn't give me the H. They didn't give me the H. They gave me HCl. Yeah, you're way too far into this course to drop it now. Sorry, you gotta put up with me. Sorry. All right, now. They did. They did give us the H. Yes, they did. No, they didn't. They gave us the HCl concentration. Don't give me the H. Uh-huh. Mm-hmm. Mm-hmm. HCl. It's a strong acid. You gotta know them. You just have to know them. Well, what does that mean? So what? How does that help me? Well, this is the concentration of the HCl, and it completely 100% ionizes, breaks apart, meaning that you will get that concentration of H and that concentration of Cl, which doesn't do anything because it's just bleh, the Cl's hanging out. But if I get that concentration of hydrogen, I got me some hydrogen. That is the concentration of your acid if it's a strong acid. If you're given the concentration of a strong acid, that's the concentration of your H. That goes here. So that's 0.0014. Same thing as 1.4 times 10 to the minus third. Get the same answer. Let's see what we get. So I'm going to divide one second function exponent negative 14 divided by 0.0014. Now I got a concentration of 7.14 times 10 to the negative 12. 7.12. Okay, that is my concentration of hydroxide. So I'll go concentration of hydroxide. This is an acid solution. It's a strong acid. HCl is a strong acid. So you've got water, you dump in some hydrochloric acid into it, what happens? You've got acid, right? Which means your hydrogen concentration is going to be a lot higher than your OH. That number, hydrogen, is a lot bigger than that number. That number be tiny. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 714. That's how much hydroxide you have, and that's how much hydrogen. Hydrogen wins. It does. It should. It's acidic. Okay, that wraps up a little bit about pH. That wraps up a little bit about what's an acid, what's a base, what are characteristics, how they taste on the pH scale, and doing the first calculation. All right, we'll pick it up for number 3 right after this message.